I'm going to finish the part A, then we'll move to part B, and we have also up to part C, but C is very small. So part B, part A, we're going to finish it. So this is really summary, this big picture summary of what the spectral analysis would do. So again, SYY stuff, you know this, but through the experiment, I want you to really feel it in your heart. That's what I want to do for next couple of weeks. Okay, so SYY is equal to H absolute square SXX. I talk about 20 to 30 times, and I can replace this expression as a G YY is equal to H absolute square times G XX, right? S is called the two-sided spectra, and G is called the one-sided spectra. So in any, you know, today they're all going at 2 o'clock, they're all going for what? You call it hiking? To, they don't know where they are going, 덕유산 or 수통골, but I decided not to because they're supposed to leave at 1:30. 1:30 is the middle of the class. I don't want to have a makeup class. So I said, I'm going to stay. So then they said, okay, we'll leave at 2 o'clock. I decided not to go anyway. That's what the message said. We are leaving at 2 o'clock. I said, okay, go ahead. I'll stay. Okay, so SXY is a cross spectrum. This is the last chance. Then in part B, I'm going to really freely use all these definitions and all that. And in diagram, this is H. H is a transfer function or frequency response function in complex domain, and input and output, excitation and response. Shaker point. This is a transducer point to pick out the output or reading. And this is how to handle the non-zero mean value. You have excitation, okay, which has a non-zero mean. Mu x is not equal to 0. Mu x has some value in it. Then when it goes through the system, H, then how do you compute the mu y? Okay? So mu y, I'm not asking you to remember, but this is the mean value of the response. Mean value, remember, mean value is a DC value, which is a static value. In the frequency domain, static value occurs at f is equal to 0. F is equal to 0, no oscillation, no frequencies, no cycle per second. So H at f is equal to 0 times the mu x. So straightforward. So mean value in frequency domain is a spike. Not f is equal, at the f is equal to 0. When f is not 0, then that's a sinusoidal function. So only we concern for the mean value is this is f. So this is like S, Y, Y. This is f is equal to 0. Then mean value occurs right here, which is equal to the mu y at f is equal to 0. Others, f is equal to, at f1, what is value? This is amplitude, let's say y amplitude. This is amplitude. This is amplitude of sine function or cosine function, or you can say harmonic functions, okay? That's what that is. Gamma xy square expression, remember. Gamma xy, x is a measurement point, y is a measurement point. Then, by definition, this is a gxy absolute square, that's real, and gxx real, gyy is real. Then gamma xy square are real, which is called the coherent, ordinary coherence function, which is a measure of noise contamination. I talked this about 10 times. Or you can express using the S rather than G. One-sided, this is a two-sided spectra. It's a factor of 2 is involved. In the experiment, you are not dealing with S. For the experiment, you are dealing with a G, because F has to be always equal to 0 or greater than 0. Okay? Negative F has no meaning in here. And the range of the gamma xy square is between 0 and 1. If it's a 1, gamma xy square is equal to 1 means no noise contamination. When gamma xy square is 0, then that's nothing but the noise. No real signal. So that's what this case is. So here is x and y. This is a system. So h is, I always call like a transfer functions or frequency response function. This shows the characteristics of the system. Okay? So you have to know characteristics of the system. That's the reason the measurements takes place always. Put at least the 2 channel. Then you put the one side to the other side. Along the path, it has a path in there. Then you can determine the H. Then once you determine the capital H, then you can determine subsequently the impulse response function. How? Take an inverse Fourier transform of H. Then you will have a small h tau, right? So when you determine the h, then you learned the characteristics, system characteristics. If the system is Yachin, then you can really tell what kind of the dynamic behavior of your Yachin would be. So that's what the beauty is. Characteristic, dynamic characteristics is what you can determine. And this is xy square is 1. Why? No noise in there. Straight input and output, no noise in there. In this case, this is a summation sign. This is a transducer location or pickup location. Here is N is a noise. In the output noise in this case, I didn't say whether this is uncorrelated noise or correlated noise, but noise is in there. And we learned for the case N is the extraneous, which means coming from the third world. So uncorrelated, independent noise is coming into the system. Or this could be an electronic noise in the transducer, vice versa. Then you learned, for last few weeks, gamma xy square is 1 minus GNN over GYY. Usually GNN is unknown. Sometimes it's calculatable using the measured the signal or measure the spectra. So in this case, when G and N is nothing, then this is 0, then this guy will be 1, which means no noise. If this is a full of noise, if this is a large, then maximum it could go is up to GYY. Then this is 1 or greater than 1, but greater than 1 doesn't mean anything. And even not possible to have a greater than 1. So if this is a large, then 1 minus maximum is a 1, then 0, which means nothing but noise in the system. You have nothing to measure the real signal. This is output noise. This is input noise. Input noise, but again we study the case M is uncorrelated noise. Okay, so this similar setup. Then you have 1 minus GMM over GXX gamma XY squared. Gamma is a very useful quantity. And in the experiment, I'm really anxious that you can really involve before you finish the semester. Maybe at least I can put it out some nice final exam problems, you know, not threatening you to just get the experience of use of those. Gamma XY square, you will see that in your final. Okay, so output noise, input noise. Now here is what? We have done it. This is input and output noise. That's about all I have done it. So, by going through quite details. So U, V, if you take a gamma U, V square, what's the value? Gamma UV, 주성. Gamma UV square. 1, that's absolutely nothing to hesitate. It's 1. Okay? No noise in the system. So this is output noise. This is input noise. Then this is what we derived that expression, gamma XY square. This is, what do you call this? GMM over GUU. Input noise to signal ratio, okay? And this is output noise to signal ratio, right? So yes, yes. And whenever you see H absolute, which is a magnitude, which is called the gain factor, always called. So he said the system gain factor because H represents here the system. Okay? Whether it's squares or not squares is immaterial. There's a gain factor, system gain factor, magnitude. And another quantity for H is the phase. Okay? The other one is phase. Then if you know the magnitude and phase, then you can always go back and forth from time domain to frequency domain. You remember this, right? H, how to measure the H or compute the H. One is using the autospectra, or power spectra is the same as autospectra. Okay, suddenly I remember when we play around the dynamic signal analyzer. Dynamic signal analyzer, there is if you check the soft button. You call it soft button? You can press it, then menu changes. Then as the menu changes, you can look at the, let's say, source. Source means type of the signal you can generate. Then type of the source, in the source, there is a, when you push the button, there is a new menu coming in. Then one case is, of course, sine sweep. Then some cases, random noise. Random noise, of course, if you look at the signature in the time domain, here, let's say, xt, then, of course, it's random. You know, you have lots of the oscillation, not the sign. It's random. Random means when you throw this into a frequency domain, then you can have f. This is x. If you set the f max as, let's say, 100 Hertz, if you set the knob as maximum frequency as 100 Hertz, this time domain signal is combination. Amplitude is that much. This is, let's say, x bar. Okay, it's a whole mix. For example, if you pick out this is 1 Hertz, if you pick out this 10 Hertz, you know, if you set maybe start from 0, 5, 10, 15, all the way. I'm just telling the relation. What that means here, if it's a 5 Hertz, you have the record, this is T, and this is X. The 5 Hertz sinusoidal function is there. 5 Hertz. Height is X. Height is all same. And the next is at, let's say, 10 Hertz, which means it's, it could be something like this. Frequency is a double, then half the here, I mean, whatever, right? 2, if it's a 15, you can have the much higher frequency, 3 times. This is 5, 10. It's a whole different combination. But when you overlap, this is 5 Hertz signal, 10 Hertz signal, 15 Hertz signal, whole thing, phasing is random. What does it mean? Phasing is random. It's not start everything nicely at t is equal to 0, at amplitude is equal to 0. No, phasing is all random. You can generate the phase using random number generator. Usually you can do in the box, instrumentation box. It's just put the phasing as a random. Okay? Then regardless, if you throw this into the random noise, this is random noise, into frequency domain, it's going to be a step function. Okay? Of course, it's not nicely constant amplitude. There could be a little bit zigzag, but it's uniform. Okay, random noise. Random noise. In time domain, this is in frequency domain. So what does it mean here? So you have to think about all that in the experiment. In the experiment, we know that SYY is equal to H squared SXX. Okay? And if this guy is random noise, you apply the such a step function. This is f. Step function multiplied to the transfer function, dynamic behavior function of the system. Of course, this function, if it's a discrete system, if it's a 2 degrees of freedom system, then you have like 2 peaks. This is f, and this is like h absolute square. Then you have 2 peaks. So if you multiply this guy to this guy, this is this guy, then resultant would be what? Resultant would be similar to this. Make sense? Say yes, makes sense. So, okay, that's good. To determine SYY, output spectra, okay, output power spectra, then this is a transfer function. This guy is this, you multiply this, you will get that result. Then you can tell, the resonance occurs at the frequency very close to natural frequency or first modal frequency. One lab, I want you to do this because you did not do in the vibration class at all. So that's what I want you to do, this. One, you have more than 2 chances because, you know, if you want to go down to lab and do that, you're always welcome. I want you to spend at least 2 to 5 hours. Okay? As long as you want, play around. But I'm going to show you all the buttons, what that does. And Zhongwan is my student, and I want him to lead. But I'll be there all the time. In my office, if you call me, I'll go down there. It's cold. You have to wear some jacket down there. It's cold. You can catch cold if you wear like choro. So you will gain the experience through this stuff. You have to go, has to do it, okay? And that's why I'm, at the same time, we conduct a class, and I'm going to give you all the information on the experiment to do, then I don't have to explain much. Then you can go right down there. I'm going to show you how to use a dynamic signal analyzer, then you're on. But we can't print it right now. We don't have a printer to hook up to HPIB interface. Okay, so don't have a plotter or anything. So until Zhongwan find out, I'm giving him a pressure, isn't it? That's I'm a bad guy, but he will do one. You're a KAIST student, so under the name of the KAIST students, you should do it, right? But don't climb up to the top of the building. Never. Okay, never ever. Okay, so, okay, where am I? That's what the H stuff, you will, I'm not sure whether you have a time to manipulate that instrumentation box. I call the DSA, Dynamic Signal Analyzer. Whether you have a time or you already learned the basic programming, you can program right in there. Then you can manipulate using the DSA rather than using your MATLAB and do all the calculation. But we'll see. But anyway, at least this year, I feel we are lucky. to be able to start using DSA. That's very, very good. Okay, so H absolute A square, HA absolute square, this is using autospectra, GYY, GXX. Then this is a cross spectra, okay. This is using GXY. You will do the both. You will conduct the experiment. You can take out the BNC cable any way you like, and so on. Maybe Friday. Well, you don't have to. I don't have to announce it. Maybe Friday we may go down and show the experiment. We'll see. This afternoon, maybe Chong'an and I will go down. Maybe no, Myung-won is coming to my office. We'll see. We can decide. All right. So this and this and this. This is three equations you understood well. I said you understood. And HA and HC, as you look at that, which give you a lower estimate when you estimate the H value. Does it make sense the way that I raised the questions? HA, HC, which means HC means what? Estimate the H using cross spectra. Another case, HA is estimate H using power spectra, or called autospectra, which give a lower estimate. Which give a lower estimate, in other words. I think the way I raise questions looks a little bit weird, but I'm going to go back to here. This equation can tell you. This is in page what? Page 14. This guy has to be less than equal to 1. Then HC has to be lower than HA, right? So this should give, HC should give lower estimate for frequency response function than HA. Make sense? Say yes. Yunsuk, yes or no? Yes. Don't care? No. You care, right? Yeah, okay. That's what this is. And, this is all I wrote here. Lower estimate for H, because this is less than equal. And here, HA is equal to H absolute square. What's H? H is GYY over GXX. What's this? XX and Y, excuse me. YY is measured, right? That's a measured G, right? G, YY, which is in the output. That's a measured output. And GXX is measured input. H here is a measured quantity here. That's what the GYY over GXX. 2 transducer. One shaker. 1 transducer. Got it? Got it. Measured. So I said here, this is a give bias arrow. When you can declare this will give you bias error or unbiased zero. When noise term is there, that give you the bias error. That's a bias estimate. This will give you the bias estimate because it has a GNN, GMM. Okay? Noise term is involved here. And here is independent. This is wrong. In your note, take a look at this. Is UU is wrong. This should be GNN. Is it your note GNN? This should be GNN. Independent of output noise here. There is no GNN. It's only GMM. This GMM is input noise spectra, right? MM input. And here is independent to GNN, output noise spectra, right? So this is wrong. UU is wrong. This should be NN. I corrected my note, but this is still some mistake. So nobody is perfect. So this is about all the summary for last 2 pages, okay? Any questions? Yeah.
I think that is also wrong.
Oh, which is wrong?
That is.
Let me see. Yeah, Could it be? Could it be? Yeah, let's see. Could it be? Spot. Which is wrong here? Let's examine that. This guy?
Yeah, they should be equal to GVV over G.
Very, very good. However, the M, input noise, N, output noise, they are the uncorrelated noise. If it's uncorrelated noise, if you associate N or M with a signal U or V, then that's a 0. Because uncorrelated, then this is true for that case. So if you look at this case in the couple pages before, then you see that. Well, let's look at together. I can't afford that misunderstand and reasoning behind. You should. I said GYY is equal to H square GXX. What you're saying is this should be as GVV is equal to H square GUU. Correct? True, right? My answer is yes, but depend. I'll show you how. It's in the previous page, couple pages before. So this is H. If this is the case, if it's U, this is a V, then this equation holds true. If this guy is X, this guy is Y, this holds true. But now, if you look at input-output noise, I think we have circuit, as I recall. This is a V, this is N, that's a Y, of course, function, right? I think left hand side is like UT. We didn't go through the diagram where the noise goes through the system is coming in part B. So this is the one I think we look at. This is the system we deal with, right? Always think this way. This guy is uncorrelated. It's coming from the third world, okay? This is uncorrelated. Okay? When this guy associates with this guy or this guy or this guy, that's all equal to 0. And if you look at this GYY, if you look at, before getting into GYY, always look, going through the process the way I do, then you will not screw up. So if I just look at the Y here, which is equal to V plus N in frequency domain. Comfortable? And YY star is equal to V star plus N star, the V plus N, right? And this is equal to V star V plus V star N plus N star V plus N star times N. Make sense? So now noise, any term involved in noise, so this is equal to GYY is equal to GVV plus GVN plus GNV plus GNN. So I'm gonna, this is weird. Anything associated with a noise is out. Extraneous noise, uncorrelated noise, it's just coming from the third world. Nothing to do. Has nothing. This is really not 0 usually. GNN usually not 0 when noise is in there. But in this case, I don't want to assume any heavy assumption. But what I did here is, this is really 0, but this is questionable. Let's put it that way. Then now GYY is equal to GVV is equal to H times the U. This is H times the GYY is GVV, right? So in this diagram, GVV is H times U. So a little bit concerned here. Of course, G, H times G U. It bothers me a little bit, but you take a look at it. I screwed up a little bit here. But let me check quickly up there. Up here, some assumption right here. What's this? Let me see. This guy is right out there. Let me see the input-output noise in there. Input-output noise together. This is right now. This is it, right? Yeah. So just to quickly review together. This is the case, right? Uncorrelated. Watch carefully here. Then VV is H squared GUU. UV is H times UU, measured quantity here, which is only gamma. This is gamma HA. I'm just checking quickly to see the derivation stuff. This is what I really over-mentioned here. Mentioned right here is what this is plus this. This is that. Okay, what I can do, if I can drive, you drive, okay? What I can do is this. What I can do is drive this guy first, get the relation, which I can say this guy is GXX, correct? You see it? This, right? Okay. Then XY, because what I have to prove is this relation is same as that relation. That's what I want to prove it. And X here is U plus M. Y here is V plus N. So this is a star. If anything wrong, you let me know. This is U absolute V plus U, this guy, N plus star plus M start. N. Is it okay? So then noise terms GXY is equal to GUV plus GUN plus GVM. You can flip this plus GMN. This guy I can say 0. This guy I can say 0. M and N are no correlation each other. I can set that equal to 0. Then I can say GXY is equal to GUV. Makes sense, uncorrelated. But I'm trying to prove that this guy is equal to that guy. This guy is, that's what I put this guy right in there. Y star Y is GYY. Then this, and this is not equal to 0. Okay, 152 is a good assignment. So you should prove very easily. And this relation is same as that relation because X, the M is uncorrelated. U is, I'm sorry. All the noise is uncorrelated, should not come into picture, but you do it. Then I'll think about it. It should be very simple. Youngbin, okay? Take a look at this relation. Yungyu, take a look at it. Prove it, prove. This is nothing but true because UV is right there. Question is, when you tap here, so how can you say this is equivalent to saying that relation? This relation, how come this is equal? That's what I want you to prove. I'll look at myself also. Then we'll talk. Today is Friday. Okay? Sometimes instructor stuck, but this portion you have to eliminate. So that's what proof should be. Okay, well, I think another group may come in, so we'll vacate the class. All right, so I'll see you on Wednesday.